Unit 3 Review, Question 42. Determine whether the numbers are prime or composite. If it is composite, show at least one factor pair of the number besides one in itself. If it is prime, show the numbers you tested and the results of your division. Okay. So we're given 51 and 79, and just to review, our goal is to determine whether a number less than 121 is prime or composite. So there's a restriction on using this process, but notice both of our numbers are less than 121. We're going to use the fact that a number less than 121 is prime if it is not divisible by 2, 3, 5, or 7. So all we need to do is check if they're divisible by those numbers. So I'm going to list them: 2, 3, 5, 7. Now I'm going to divide 51 by each of these numbers and see if there's a remainder. So 51 isn't even because it doesn't, so it's not divisible by 2, but we'll check it anyway. So no. Is 51 divisible by 3? And it is. It equals 3 times 17. Now here's the good news. We don't even have to check 5 or 7, okay? Because since we found that 51 has a factor other than 1 in itself, namely 3 and 17, that means it's composite. It is not prime. So we're actually done. We don't have to check all of them once you find a factor besides 1 in itself. So composite has 3 and 17 as factors. Okay. Now let's see if 79 is prime or composite. So 2, 3, 5, and 7. Okay, well, let's notice it's not divisible by 2 because it's not even. So I'm going to cross this out. Not even. Okay. And it doesn't end in 0 or 5, so it's not divisible by 5. So we're going to cross this one out. It ends in 9, so it's not divisible by 5. So using those ideas, we only really need to check 3 and 7. So let's divide 79 by 3. And notice there's a decimal fraction, which means there's a remainder, so it's not divisible by 3. And let's check 7. 79 divided by 7, that'll be 11, and something left over. So it's not divisible by 7. Okay. So 79 is not divisible by 2, 3, 5, or 7, so it is prime. Okay, and these are the numbers we checked. Let's look at the next slide. Find the prime factorization for the given numbers. Write the final results in both exponential form and factored form. So to find prime factorization, we use the process of factor trees. So we're going to look at 72, and we're going to rewrite 72 as the product of any two factors we can think of. So you may think of 8 and 9. I'll start with 8 and 9. 8 times 9 is 72. It doesn't matter which you start with, you'll always get the results, the same results. So now I look at 8. 8 is not prime, so I'm going to keep factoring 8 along this tree. 8 is 2 times 4. Now 2 is prime, so once I get a prime factor, I'm going to circle it. That's part of the prime factorization. Now the 4 I have to keep going. So 4 is 2 times 2. Since 2 is prime, I have fully factored this branch. Now I have to go to 9. Well, 9 is 3 times 3. 3 is also prime, so I can circle those. And the circled numbers all multiplied together are my prime factorization. So the factored form, you want to put these in increasing order. So we have 3 factors of 2 and 2 factors of 3. Okay, just to verify, notice if we multiply these, 2 times 2 times 2 times 3 times 3, the result is 72. So this is 72 written as the product of only prime numbers. Now in exponential form, 3 factors of 2 is 2 to the third. Then connect them with multiplication. 2 factors of 3 is 3 squared. Let's look at the next one. Okay. So 60 is, let's write this as 10 times 6. Again, any two factors of 60 will work as long as their product is 60 to start with. Now 10 is not prime, so we're going to keep factoring. 10 is 2 times 5. Both 2 and 5 are prime, so I'm circling them. Now we'll go to this branch. 6 is not prime. 6 is 2 times 3. 2 and 3 are both prime, so I circled them. So the prime factorization is the product of these four numbers. I'm going to put them in increasing order, so start with the 2 factors of 2, then 3, then 5. The exponential form is 2 factors of 2 is 2 squared, and then we'll just write 3 times 5. They're each to the first power, but we don't write the first power just because it looks a little messy. Let's look at the next one. Find the greatest common factor of the given numbers. So here we have 8 and 20, and we learned 2 ways to find the greatest common factor, and I'm going to use the way that always works despite the size of the numbers. So we're going to find the prime factorizations. So 8 is 2 times 4, and 4 is 2 times 2. So the prime factorization of 8 is 3 factors of 2. Now let's find the prime factorization of 20. Well, 20 is 2 times 10. 2 is prime, so I'm going to circle it. And 10 is 2 times 5. So the prime factorization of 20 is 2 times 2 times 5. Now their greatest common factor, once you have the prime factorizations, you want to find any factors they have in common, including repetitions. So here's 1 factor of 2 in common, and they actually have 2 factors of 2 in common. Okay. This has another factor of 2, but 20 does not. 20 has a factor of 5, but 8 does not. So their common factors, prime factors, are 2 factors of 2. So 2 times 2, which is 4. Okay. So this is the prime factorization method. The other method is list all the factors of 8 and 20, like we did when we did factor pairs, and find the greatest factor they have in common. Okay. 30 and 75. So I'm going to find their prime factorizations. 30 is 5 times 6. 5 is prime. 6 is 2 times 3. And 2 and 3 are prime. So the prime factorization of 30 is 2 times 3 times 5. Now let's do 75. 75 is 3 times 25. Again, it's also divisible by 5. You could use that. 3 is prime, so I circle it. 25 is 5 times 5, which are both prime. So 75's prime factorization is 3 times 5 times 5. Now, what do they have in common? Well, 30 has a 2, 75 doesn't. 30 has a 3, and so does 75, so 1 factor of 3. 30 has 1 factor of 5, and so does 75. 75 has another factor of 5 that 30 doesn't have, so we do not include it. So our greatest common factor is 3 times 5, or 15. Let's look at the next one. Now we want to find the least common multiple for the given numbers. So we're actually going to start the same way as the greatest common factor, and then we just do one extra step at the end. So 6 is 2 times 3, so we find the prime factorizations. 15, well, that's 3 times 5. So the prime factorization of 15 is 3 times 5. Okay. Now we're going to find the GCF. I know that seems a little weird because we're trying to find the LCM, but we're going to use this to do so. Notice what they have in common is 1 factor of 3, and that's it. So their greatest common factor is 3. And then we found the least common multiple is equal to the product of the two numbers. So let's write this up here. Is the product of the two numbers divided by their GCF. So now, once we know the GCF, we can just find 6 times 15 divided by the GCF will give us the LCM. So 6 times 15 divided by 3 is 30. Okay. Another way we learned how to do this is list multiples of 6, 6, 12, 18, 24, 30. List multiples of 15, 15, 30, 45. Their smallest common multiple is their least common multiple. Okay, but this method will always work without being too time consuming. The listing multiples can work, but it can take a really long time. So 12 is 3 times 4. 3 is prime, so I circled it. 4 is 2 times 2, and 2 is prime. So the prime factorization of 12 is 2 times 2 times 3. 54. Okay, so 54 is even. It's divisible by 2 because it is even. So I'm going to do this on the calculator. So now we have 27. Okay, so that's a good plan if you can't think. This is also 9 times 6. But if you can't think of a factor right off the bat, you can check for evenness and the numbers get smaller. 27 is 3 times 9. 3 is prime. Factor 9 further into 3 times 3. So 54 is 2 and 3 factors of 3. So now let's find their GCF. Well, they each have 1 2 in common. This has another 2, but 54 doesn't. They each have 1 3 in common. 54 has 2 more factors of 3, but 12 doesn't. So their GCF is 2 times 3, which is 6. So their least common multiple is the product of the two numbers, 12 times 54, divided by their greatest common factor. So that is 12 times 54 divided by 6, which is 108.